NENOMATICA, where mathematics meets YouTube excellence. Here is the algorithm. Case 1. If r is greater than 1, then the logarithm is increasing. So comparing the logs is the same as comparing the inputs. We must also guarantee that the argument on the right is positive. Case 2. If 0 is less than a and is less than 1, then the logarithm is decreasing, so the inequality reverses, and we require that the argument on the left be positive. Why do these cases happen? Because the shape of the log changes with the base. On the left, log base 2 is increasing, so larger inputs give larger outputs. On the right, log base 1/3 is decreasing, so larger inputs give smaller outputs. That is why the inequality reverses. Example: solve log base 2 of open parenthesis 3x minus 1 close parenthesis greater than log base 2 of open parenthesis x plus 5 close parenthesis. We are in case 1 because a equals 2, which is greater than 1. That means, first, make the right argument positive, then compare inputs without flipping the sign. Finally, intersect the results on a number line. Second example: solve log base 1/3 of open parenthesis 2x plus 1 close parenthesis greater than log base 1/3 of open parenthesis x plus 5 close parenthesis. This is case 2 because the base is between 0 and 1. First, make the left argument positive. Next, reverse the inequality when comparing the inputs. Finally, intersect the results on a number line. Important reminder: when we remove the logarithms and turn the problem into a system of inequalities, we must include the domain conditions. If a is greater than 1, we require the right argument to be positive. If the base is between 0 and 1, we require the left argument to be positive. In both cases, the comparison step already guarantees the other argument is positive. Finally, we intersect all conditions to obtain the solution set. Here is the inequality we will solve. Notice it matches the starting line in the solution. Log base 2 of the fraction 5 minus 12x over 12x minus 8 plus log base 1/2 of x is less than or equal to 0. The first written line in the solution simply repeats the inequality unchanged. Next, rewrite the base 1/2 as 2 to the power -1. That gives log base 2 to the minus 1 of x. Using the property log base a to the power k of b equals 1 over k times log base o of b, we get minus log base 2 of x. Now move the minus log base 2 of x to the right side. This is equivalent to saying the left expression is less than or equal to log base 2 of x. Because the base 2 is greater than 1, we can remove the logarithms without flipping the inequality sign. We must also include the domain condition that the argument of the left logarithm is positive. The image records this as a system. Solving that system, the solution set simplifies exactly as shown. 5/12 is less than x, and x is less than or equal to 1/2. Finally, we write the answer in interval notation. This matches the final line in the provided solution. Example: in this lesson we will solve a logarithmic inequality step by step. The problem is, log base 3 of x squared minus 2 is less than log base 3 of open parenthesis 3, halves times the absolute value of x minus 1 close parenthesis. Step 1. Because the base 3 is greater than 1, the logarithm is strictly increasing. So we may compare the arguments directly and keep the same inequality sign. We must also require the left argument to be positive. That gives the system shown. Step 2. Write x squared as the square of absolute x. That keeps the expressions non-negative and lines up our next substitution. Step 3. Substitute t equals absolute x. Then t is greater than or equal to 0. Move terms and clear the fraction in the first inequality. Step 4. Factor both quadratic expressions. The first is a difference of squares with roots plus or minus square root 2. The second factors as 2t plus 1 times t minus 2. Step 5. Solve each inequality on a number line and intersect with t greater than or equal to 0. We place critical points at minus 1/2, 0, square root 2, and 2. From the first inequality, t lies outside the open interval from minus square root 2 to plus square root 2, and keeping t non-negative gives t greater than square root 2. From the second inequality, we get minus 1/2, less than t less than 2. Intersecting these gives the final range, square root 2 less than t less than 2. Step 6. Replace t by absolute x. That gives square root 2 less than absolute x less than 2. Splitting the absolute value inequality, x lies between square root 2 and 2, or between negative 2 and negative square root 2. Summary. We used the monotonicity of the logarithm with base greater than 1 to compare arguments, rewrote x squared as absolute x squared, substituted t equals absolute x with t non-negative, factored and solved two quadratic inequalities, intersected the results on a number line, and finally converted back to x. The solution set is the union of the open intervals from negative 2 to negative square root 2 and from square root 2 to 2. In this example, we will solve a logarithmic inequality step by step, exactly following the structure in the provided solution. Our problem is log base sine of pi over 3 of the quantity x squared minus 3x plus 2 is greater than or equal to 2. Step 1. Replace the base sine of pi over 3 with square root of 3 over 2. Then rewrite the right-hand side as 2 times log base square root of 3 over 2 of square root of 3 over 2. Step 2. Apply the power rule, so the factor 2 becomes an exponent. Step 3. Because the base is between 0 and 1, the logarithm is decreasing. So, removing the logarithm reverses the inequality, and we must also impose the positivity of the argument. Since the right side becomes 3/4, we obtain the system shown next. Step 4. Solving these gives the final intervals. To visualize the intersection, let's use a number line. First, the green segment shows x between 1/2 and 5, halves inclusive. Next, the red regions show x less than 1 or greater than 2. Finally, the purple pieces highlight the intersection, from 1/2 up to, but not including, 1, and from just greater than 2 up to 5, halves inclusive. Therefore, the solution set is x is greater than or equal to 1/2 and less than 1, or x is greater than 2 and less than or equal to 5 halves. 1/2 and less than 1, or x is greater than 2 and less than or equal to 5 halves. Our problem is log base x squared of 2 plus x is less than 1. Step 1. Rewrite the right side as a logarithm with the same base. We use the identity k equals log base b of b to the k. So 1 equals log base x squared of x squared. Therefore, log base x squared of 2 plus x is less than log base x squared of x squared. Step 2. Establish the domain and base conditions. The argument must be positive, 2 plus x greater than 0, hence x greater than negative 2. The base must be positive and not equal to 1x squared greater than 0, so x is not 0, and x squared not equal to 1, so x is not plus or minus 1. Combining these, our working domain is open interval negative 2 to infinity, excluding negative 1, 0, and 1. Step 3. Case 1x squared is greater than 1. Then the logarithm is increasing, so the inequality direction stays the same. 2 plus x less than x squared. Move all terms to one side, x squared minus x minus 2 greater than 0. Factor. Left parenthesis x minus 2 right parenthesis times left parenthesis x plus 1 right parenthesis greater than 0. This holds for x less than negative 1, or x greater than 2. Intersect with the domain, and with x squared greater than 1, and we obtain x in open interval negative 2 to negative 1, union open interval 2 to infinity. Step 4. Case 2x squared is between 0 and 1. Now, the logarithm is decreasing, so the inequality direction reverses. 2 plus x greater than x squared. That is x squared minus x minus 2 less than 0, which means x is strictly between the roots negative 1 and 2. Intersect with 0 less than x squared less than 1. That is x in open interval negative 1 to 0 union open interval 0 to 1. Therefore, S2 equals open interval negative 1 to 0 union open interval 0 to 1. Step 5. Combine the two cases. The final solution is S1 union S2x in open interval negative 2 to negative 1, union open interval negative 1 to 0, union open interval 0 to 1, union open interval 2 to infinity. Here is a number line view with the intervals highlighted. Recap. we matched the reference solution. First, we rewrote 1 as a logarithm with base x squared. Second, we enforced the domain x greater than -2 and excluding -1, 0, and 1. Then we split by the base. For x squared greater than 1, we solved a greater than 0 quadratic. And for 0 less than x squared, less than 1, we solved the same quadratic, less than 0 with the reversed inequality. Finally, we took the union to get the full solution set, quadratic, less than 0 with the reversed inequality. Finally, we took the union to get the full solution set. In this example, we will solve a logarithmic inequality step by step, matching the exact algebraic flow from the reference solution. And we will also make the domain conditions perfectly clear. Here is the problem statement. Step 1. Use the product rule to split the first logarithm and rewrite the unusual bases 1/3 as 3 to the power -1 and square root of 3 as 3 to the power 1/2. That turns the given statement into this line. Step 2. Convert each remaining logarithm so that the base is 3, log base 3 to the power -1 of x plus 2 equals negative log base 3 of x plus 2, and 1/2 times log base 3 to the power 1/2 of 7 simplifies to log base 3 of 7. Step 3. The plus log base 3 of x plus 2 and the minus log base 3 of x plus 2 cancel. We are left with a single, simple inequality of logarithms with the same base. Step 4. Inequality of logarithms with the same base. Step 4. Because the base 3 is greater than 1, the logarithm is increasing, so the inequality direction is preserved when we drop the logs. That gives x plus 4 less than 7, or x less than 3. Step 5. We must also enforce the domain from the original inequality. The terms inside logarithms must be strictly positive. We have 2 requirements. First, x plus 2 must be greater than 0. And second, the product x plus 2 times x plus 4 must be greater than 0. Since x plus 2 is positive, the product condition forces x plus 4 to be positive as well. Therefore, the domain reduces to x greater than -2. Step 6. Combine the inequality x less than 3 with the domain x greater than -2. The final solution interval is open parenthesis -2, 3. Now, let's visualize it on a number line. Therefore, the solution to the inequality is all real x strictly between -2 and 3. In interval notation, that is open parenthesis -2, 3. Recap. We used 3 big ideas. 1. Product rule for logarithms. 2. Rewriting the bases 1/3 and square root of 3 as powers of 3 to align the base. 3. Dropping logs safely because the base is greater than 1, and finally intersecting with the domain. In this example, we solve a logarithmic inequality step by step, matching the exact structure from the provided solution. First, here is the example. We'll work with this inequality and transform it carefully. Step 1. Isolate the logarithmic terms on opposite sides. We'll add 2 log base 1/3 of x minus 4 to both sides. This yields log base 1/3 of x squared minus 6x plus 18 is less than 2 log base 1/3 of x minus 4. Step 2. Apply the power rule for logarithms. A constant times a logarithm becomes an exponent on the argument. So 2 log base 1/3 of x minus 4 becomes log base 1/3 of x minus 4 squared. Step 3. Remove the logarithms correctly. Because the base 1/3 is between 0 and 1, the log function is decreasing. That means inequalities reverse direction when we drop the logs. Also, every log argument must be positive. Therefore, we obtain a system x minus 4 greater than 0, and x squared minus 6x plus 18 greater than quantity x minus 4 squared. Next, expand and simplify the quadratic comparison. The square of x minus 4 is x squared minus 8x plus 16. Substituting gives the system x greater than 4, and x squared minus 6x plus 18 greater than x squared minus 8x plus 16. Now cancel x squared from both sides and solve the linear inequality. Bring like terms together. We get 2x plus 2 greater than 0, which means x is greater than -1. Finally, intersect the 2 conditions. If x is greater than 4 and also greater than -1, the stricter requirement dominates. Therefore, x is greater than 4. In interval notation, The solution is open parenthesis 4 to infinity. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.